How about now?
Well, no, I've got a separate one that goes to the proceedings. Sorry.
Right. So in terms of what we're going to talk about today, I'm going to talk about what was the problem statement that the New York City provided to us, what their goals were, what assets they provided, the research we did in terms of exploring the alternatives, and specifically what were our criteria for selecting technology, what technology we ended up selecting, the architecture that we ended up with, what we've accomplished so far, and what we're hoping to do in the future. So just to give a little bit of background about the New York City Department of Transportation, it's New York City. They're responsible for all the boroughs. They've got 6,000 miles of roadway, 800 bridges, which actually surprised me. They also are multimodal in that they support the Staten Island Ferry, and then that leads to 12,000 intersections and 300,000 streetlights. So it's a fairly big network for a municipal one. And the problem that they reached out to us for is that currently they're doing their over-dimensional permits for truck trips. They're doing it fairly manually, so they ask people to either mail it in or bring it in person, and people end up hiring courier services, and it's not a very efficient process. And where routing comes into play is that the trucks have to the permit has to come back with a route specified. So it has to have the start point, the end point, all the streets that they're going to travel on. It needs to take into account the vehicle's weight, the distribution of content on the truck, and then it has to, of course, has to take into account road conditions and closures for the time when they're going to be traveling. So just more specifically, 800,000 pounds and above is when these trucks start to need to be permitted. And then the specifics depend on the axle spacing, the configuration of the vehicle, whether or not it's carrying hazardous materials, et cetera. And I don't have numbers for the city, but the state issues over 100,000 of these every year. So the goal of the project was to create a point-to-point routing system that would, when possible, use designated truck routes, and I'll show you a map of those in a moment. Take in the address, the point of interest, latitude, longitude, and then route them around barriers basically in real time or near real time. It also, of course, had to take into account those height and weight restrictions, turn restrictions, which are sometimes time-based, and then just any other blockages of the road, for example, like permitted construction or known blockages. And it had to spit out route segments and turn-by-turn directions. So those are the specifications. So what do I mean by blockages? Well, this was the most fun example I could find from the last couple of months. Pope Francis visited the city, and they shut down the street network from Central Park West over to Columbus and then down to Broadway. So a large segment of the city was shut down. So, of course, permits that were issued for this day had to take this into account with minimal downtime to the system. So I know this is hard to make out, but I just wanted to show that they issue a PDF right now that shows what the truck routes are. So it's a grid on top of the overall street grid. So it's not entirely sparse, but many streets are restricted for these large vehicles, except for when they're actually approaching their final destination. And of course, you have to take into account in New York the tunnels and bridges. A lot of them have height and weight restrictions for safety purposes. So the asset that the city had that they provided to us is that they have a topologically complete street network. So they have nodes and segments. They have connectivity between them. And the Z-levels are taken into account. So you know that if you're on a certain deck of a bridge, that it's going to connect to the on or off ramp correctly. So they have a pretty good data set there that they maintain pretty fastidiously of the whole process around it. And of course, it contains the street names, the truck route information I alluded to, and then also points of interest. And when I'm talking points of interest, I'm mostly talking about entry points and exit points into the city. Those are the ones they're mainly concerned with. They asked us to look at software. They specifically specified that it'd be low or no cost, and they were hoping for open source. They wanted software that would support bringing their own data. So that was an important criteria. They were less interested in OpenStreetMap or the HERE commercial data set, that kind of stuff. They wanted it to be a system that could be flexible in near real time, so they could enter a blockage and have it routed around almost instantaneously. This next one, performant, they wanted it to be performant, but they were willing to trade that off for flexibility. And so that's what makes this case study a little bit unique, and I'll talk about that in a moment. And then lastly, they insisted that it have a low cost of integration. And for them, that meant we had to take advantage of the resources, the developer resources they had. So they have .NET, C# developers, What they don't have are C++, a lot of Java developers. They also have front-end developers. And then they have a number of people who can do SQL as well, and that ended up being an important criteria. So these are the open source software that we looked at for routing with them. And I'm going to talk a bit about each of them just in terms of how they met the criteria or didn't meet the criteria we were looking at. So the first one was open source routing machine. It was fast. It uses contraction hierarchy indexing, which I'll talk about in the next slide. Easy to install. They have cost profiles, which are, for those of you who saw the Valhalla presentation before, what that refers to is the ability to match tags, OpenStreetMap tags typically, to the cost of traversal, the speed limit that the vehicle has to follow, or anything else that would cause you to, the costing model to change. And these are easily customizable, so that was an interesting feature. They use Lua scripts. So they didn't need, the Lua scripts are straightforward enough that they didn't need specialized programming knowledge necessarily to make changes to them. And then they also support partial indexing. So the system has to go down for a time while the indexing happens, but you don't have to re-index the entire system fully. You can trade off some performance for a little bit more flexibility there. So that was an interesting feature. I'm not an expert in contraction hierarchies, but this link, and it'll be in the slides that are downloadable, is an excellent visualization of contraction hierarchies. Essentially what it is that the routing graph is pre-processed. It's indexed, so that intermediate nodes that are known to be part of shortest paths are dropped out for certain steps in the routing solution. What this leads to is great performance. So that's a lot of the systems now that are touting their performance are using this. So you can see that going from node A to node B typically passes through node C. So rather than including that in your solution at the end, instead you drop C out, you contract it out, and then you just know that the cost is 5 by adding those two segments out. So I mentioned, I'm not going to go into any detail. This is just I cut and pasted from the truck Lua script that they provide. So one thing that all of these profiles and a lot of these software seem to have in common is they have two parts, right? They have the constants, which are the cost profile stuff of going over street segments, and then you also have support for functions as well, so that you can dynamically have the interplay, let's say, between multiple tags, or do different kinds of calculations for blockages is another example of what they use it for. So this is where it was less of a fit. It's OpenStreetMap centric, so it was challenging. It would have been a very large challenge to convert Lion into OpenStreetMap for these purposes. It still requires downtime to do the partial contraction. So if we do a change in the data, we introduce a blockage, or do other things, and you still have to bring the system down even if it's just for a few moments, and that represents a challenge. And then this is less important because the performance was less important to them, but it's still, if you're doing partial contraction, then you're losing some of that performance benefit because you're only maybe contracting out 20% of the nodes that you could have otherwise. So that was another challenge as well. So again, those of you who sat through the Valhalla presentation that was before, this will be a rehash a little bit, but Valhalla, we liked it because it was, the city liked it, we liked it because it has it's fast and has a low memory footprint. They have that really intriguing route tile technology that will ultimately support offline models with, in mobile, so that was an interesting feature. They have lots of costing models, which again was introduced in the last talk, and they can be applied at runtime as well. So there's minimal performance, or there's really no downtime or performance impact to applying these profiles at runtime. So there's potentially a lot of flexibility there. And this is an example, so you can see it's very similar to the Lua, and this is done in C++. So this is how Valhalla does it. So if you want to introduce a new profile, you would write it with these constants and with these functions written in C++. So the challenges, as I hinted at earlier, C++ coding is not something that the city has a lot of capability in it. This would have increased the cost of integration. And they're built around the OpenStreetMap data schema. So, and it sounds like, and having talked to the gentleman who presented previously, that they're not supporting other custom data models at this time. So again, it would have required an OpenStreetMap conversion in order to make it work. The next software we looked at is GraphHopper. Again, a contraction hierarchy-based system, at least in their speed-up mode, very fast, very easy to install. It provides you, again, the option to switch between cost profiles. And they have a great Java API. So part of that Java API is that you can extend with their reader class, and you can use that then to use your custom data and convert it into their graph. And they provide you the example, of course, of OpenStreetMap, and you can do it for yourself. So that seemed like a pretty good benefit there. And then they also allow you to do on-the-fly traversal costs and turn restrictions in a mode that doesn't involve contraction hierarchy. So you can trade off speed for the kind of flexibility we were looking for. So it looked like a pretty good fit, and here's an example of the Java code for doing the flag encoder for vehicles. So again, you can introduce functions that change or even block the cost of traversing a segment. So the challenges is that the reader is great, but it would have been more resources and time than we had. It still would have been a significant effort to convert it into the GraphHopper graph. And this is less, again, the performance was not a huge concern, but you turn off speed up mode, so you lose some of those performance gains by going to the more flexible model that the Java API presents. And then, of course, there are .NET shops, so a Java code base in the long run probably wasn't going to be a great solution for them. But given other circumstances, GraphHopper might have been a really good solution. PgRouting was the last software we took a look at. Big advantages here, it has an extremely simple data schema, and I'll show that in a moment. It's in the right place in the architecture for them, so they have people who know SQL. They didn't want to necessarily maintain a new middle tier piece of software, and so they could just maintain it within the database and it'd be less effort. And then it's straightforward to implement custom traversal costs and turn restrictions when you're doing PgRouting. So I'll show that in a moment. So this is an example of a PgRouting query taken right out of their documentation that uses turn restrictions. So the table that's referred to at the very end, the from restrictions table at the very end there, it's just a table that contains the segment IDs and identifying those as restrictions. And this is the output. You get a sequence, you get the node ID, you get the edge ID, and you get the cost. So it's very simplistic. The challenges, it's way slower than the other options. Even we put in a lot of work and time at the city to try to improve the performance, but even when you didn't take into account the indexing options for the other ones, if you turn that off, they were still significantly faster than PgRouting. Other big disadvantages, the spoken language driving directions is not included. And there's no RESTful or JavaScript API either. So you're dealing with SQL, and it can be pretty raw and a challenge. So this is just a graphic we put together. I mean, there's a lot of flexibility in the ones in the upper left-hand corner, but PgRouting is the most simplistic and most flexible, and the trade-off is that the performance is the worst. And so that seems to be a theme in evaluating these software, is the more flexible you get, the more you're trading off performance in the responsiveness of your queries. So we ultimately went with PgRouting because the responsiveness was not the most important factor and because of the cost integration was lowest. Specifically, the turn-restricted shortest path piece of PgRouting. And along with that, of course, comes PostGIS. So we started to provide the city more tools to manage the Lion data set that they were running. So spatial operators, spatial indexing of Lion, and some tools to manage the topology, and I'll talk about that in a moment. And then Spring Boot specifically to build RESTful services around it. And it ended up being not a huge task to create RESTful services that called our SQL for it. And then on the front end, they are a Leaflet shop. They have people with Leaflet experience in the city, so we went with that. And we use Leaflet for base map display, for rendering of the vector elements, and for just general user interface. So this is just another representation of the simple architecture, jQuery plus Leaflet on the front end, GeoServer for some of the base mapping that we did for them, Spring and Tomcat sitting on Java, and then PgRouting on the database side. And on the upper right-hand corner is the driving directions API. So Stephen Woodbridge is a contributor to PgRouting, and he is explained at this link, and it will be in the slides, what you need to do to convert that very bare minimum PgRouting output into turn-by-turn driving directions, at least as a starting place. He also provided us with some PL, PGSQL, some functions that we used as a starting point. effectively what you're doing is you're making sure things are in the correct order, you're making sure that you get rid of duplicates in terms of segment names, and then you compute the turn angles. Those are the main things. And then there are special cases, roundabouts, for example, via points, and then special cases where the whole route is on one segment. But that's about it. So it seemed daunting, but it actually isn't that much effort to get to turn-by-turn directions with PgRouting. And so we were concerned about the roundabouts, and the New York City people reassured us there's only 6 of them or so in the city, which is shocking for a city that has 600 bridges, but only 6 traffic circles. At least for me from DC, that's very, very surprising. But Columbus Circle serves 60,000 vehicles a day, so another sense, it gives you more of a sense of the scope of the volume of traffic they have to deal with. Just a brief aside, geocoding. So we went back and forth about whether or not we could use an external geocoding service. We created a proof of concept with it where we showed them that just using PostGIS and the distance operator, you could get the nearest segment, and then you could call another function to get the percentage along the segment. And likewise, for forward geocoding, there's this project called JGeocoder, a rather old project, but it still contains useful stuff for parsing that address, pulling out the street name and the address ranges, and then using that to help you find the correct segment and derive the percentage along it, and then whether you're on the right-hand side or the left-hand side of the road. So again, it seemed daunting, but actually wasn't that big of a deal. I mentioned there was a service wrapper. In the interest of time, even though they are a .NET shop, we ended up just doing a quick Spring Boot wrapper around it. The important thing, though, is that we kept things in the bare minimum JDBC SQL calls, so we handed off to them essentially the SQL for them to do their own ASP.NET development later on. So again, that proved to be an advantage. So this is what we've got so far. We've got a system that takes in points of interest, truck routes, truck route places, lat long. It spits out turn-by-turn directions, and it spits out the route segment map display. And then it also manages their metadata as well. And by that I mean that they can click on any segment in the route, and it will tell them the connectivity, whether or not the segment is properly connected topologically to the one next to it. It also tells them whether or not it's part of a truck route and what the cost of traversal is. And the reason we created that is, not surprisingly, when we created these routes, people say, well, that's wrong. Or that's not what I get for Google Map. And so we gave them the ability, step by step, to manage it, review it, and we could convince them, actually this is why it went the way it did, and if there's a problem, maybe we can look at the data, or maybe look at the way we're calculating cost. And so the output then takes into account turn restrictions, height and weight restrictions, and then pushes routes whenever possible onto the truck routes. And so this is a screenshot from it. You can see on the left-hand side we've got the turn-by-turn directions. On the right-hand side, you've got visualization of 2 different routes, one that's using truck route restrictions, the other one is not. So the Brooklyn Bridge is restricted for height and weight and is not part of a truck route. So you end up going through the Cary Tunnel all the way around when you're traveling into Brooklyn from Manhattan like that if you have a large vehicle. So that was just an example we provided. You can also see in the bottom right-hand corner that metadata I was talking about. Very, very simple review, but we're showing them the cost. This person has clicked, I think, on the Brooklyn Bridge here, and it's showing them that it's a blockage. It's -1, so it's blocked. Gives them the segment ID, gives them more information to do an investigation. I mentioned that the model for PgRouting is very simple, and this is it. Effectively, this is it. So we extracted these fields from Lion, the segment ID, and a little bit of the topological information. That's all we needed, really. The stuff on the right-hand side is how we implemented restrictions or truck routes, which are the opposite of restrictions, effectively. All we needed was the segment IDs and a little bit more identifying information. That was it. What is complex in PgRouting is the SQL calls themselves end up being gigantic. In this case, we made it worse because we did the turn-by-turn stuff was also a PG-SQL function, so we ended up wrapping it around it. So we get these very large calls. The stuff in red in there is where we're using Java to insert the last little bits of our costing function. So I'm going to show that. So here you can see all we're doing is selecting segment IDs. I mean, this is a simplified version, but all we're doing is selecting the segment IDs from the physical restriction table and assigning it a -1, which tells PgRouting, hey, you can't go on this segment, and vice versa. Then we're giving a very small positive cost for those truck route segments. And that was all we needed really to do our PgRouting calls. So the next steps with what we're building is we need a better user interface for helping users enter truck class information. There's a lot of complex stuff that can potentially go into it. Not just the height, weight, and cargo that I listed, but also how the cargo is distributed. There are official truck classifications that we can use as well to simplify this. Speed limit and historical traffic data is stuff that's commercially available for the most part. It can be purchased from here or TomTom. That would be a good option, I think, for improving the routes if they know the specific times. Now, some of these permits are issued for multiple days, so they may not know exactly the time. But for the ones where the time is specified, that would be useful. And then right now, we just have that click interface for people to identify gaps in the topology. I think there are other tools that we could build to make that a more intuitive process for them, maybe to pre-identify, for example, where there are gaps in topology or where there are gaps in their data management. And then lastly, right now, they're just entering data into the tables. There's no reason why we couldn't have a simple map-based system for barrier creation and editing as well. So adding to the track routes or adding height or weight restrictions or closing streets just by dragging an area of a map. The last part is, I alluded to this earlier, is that the performance is poor. And one thing I think we could look into is when we are getting multiple hits, we could look at PG pooling for concurrent access. But I don't think that's going to solve the basic problem, which is that just one person running the query, it might take 30 seconds to come back, which is unacceptable. So one thing we'd like to start investigating at Boundless is partitioning potentially, to see whether or not there are partitioning strategies that we could do to distribute the graph onto multiple machines and then actually have that load be balanced that way. So I'm not sure if that would work, but that seems like the only option I can think of right now for improving the performance for the queries one at a time. So with that, throw it up and see if anyone has any questions. But it was easy to formulate a query to do. So the turn restrictions is included in PgRouting. The time element was just a matter of adjusting the SQL to say, okay, this is the known time. Then we just query the table and only pull out the ones where it applies. Anything else? Okay. All right, thank you, everybody.